And now I'm going to share the screen. Okay, so I'm in our Tuesday, November 17th, and today lecture, which is on shear and bending moment diagrams. And we're going to go over the overview in a little bit, but I wanted to point out some things that are posted. One is the shear and bending moment diagram template, and let me just pull it up. I have it opened already. And can everybody see it? Right? So this is what we went over yesterday. The first horizontal line represents the beam, and we put all the loading on the beam. And then we draw vertical lines down so that we have our shear diagram drawn right below the loading diagram. And we put V, and we put the units, and we put a 0 and plus and minus. And then on the right side, we put in the scale depending on how large the shear is going to be. And then we continue those vertical lines down to and draw a horizontal line for the moment, and we put our units, and we write 0 plus or minus, and then we put a scale here based on our moments. Then going back to the module, I also posted the problem that we did on Tuesday, so let's just take a quick look at that. And it's right here. And I'm going to move our pictures over and make this full screen. So the problem we worked on Tuesday was chapter 7, number 38. And this was our loading diagram. At A, we had a 120-pound force going down. At D, we had a 300-pound force going down. And at F, which you can't see, at F, there's a load here of 120 pounds as well. And so what we did is we looked at these external loads and we calculated the reactions at the support. At C, there was a pin. And at E, there was a roller. So we first did the sum of the moments about point E to cancel this out. And we found CY is equal to 240 pounds. We did some of the forces in the X, which resulted in CX being equal to 0. And then we did some of the forces in the Y, and we found EY to be 300. And then we did some of the moments about another point just to check to make sure we get the 240 and the 300, and we did. Okay, so that we already know how to do anyway. So now we have our template. We draw a vertical line down every time where there's a section where there's some change happening. And there's the 240 pounds here, there's the 300 pounds here, there's the 300 pounds here, and then at the end it was 120 going down. And the shear diagram followed the loading exactly. So at point A, there was 120 pounds going down. So I went down to 120. Then between A and C, nothing happened. So there was no change. I stayed at 120. At C, there was a 240 going up. So I drew my shear diagram going up 240, which brought me to a positive 120. And then from C to D, nothing was going on. So it continued at 120. At D, it went down 300. I drew a line down 300, which resulted in a negative 180. And then from D to E, nothing happens. Continue over on the 180. At E, the 300 brings me up to 120. Nothing happens here. And then at the end, we have a 120 force going down. And that's really your check, because a shear diagram always starts and ends at 0. If it was up to 180 here and you had a force of 120 going down, you would know there's some mathematical error. And then looking at the shear diagram, we realize that the maximum absolute shear that this beam is going to experience due to this loading is 180 pounds. Whether it's negative or positive, it doesn't matter. It's going to experience 180 pound force. So we have to make sure that we select a beam that could handle that kind of load in shear. Then we learned from distributed loads that the moment is really the integral of the force, right? And that's really the area, and V, the shear, is a force. So what we did is, and we colored in this, that we shaded the regions, and then I called them regions 1, 2, 3, and 4, and I put a negative when the area was negative and a positive when the area was positive. And then we calculated the areas for those 4 sections. And then in order to do the moment diagram, I start at 0. The area was 1,200 and it's a negative area, so the slope is negative. The second area was 3,000 and it was a positive area, so I go up 3,000. This area was a negative 3,600, so I have a negative slope going down 3,600, which brings me to 180. And then the last area was 180 and it was a positive area, so it comes up, and sure enough, it does close at 0, which is another check. And then we shade in the region. And the maximum moment we saw is actually, we saw a positive and a negative of 1,800. So we have to make sure that we're designing this beam to handle 1,800.
Joanne, I have a question.
Yeah, Angel.
So those areas, that is coming from the shear that we came up with beforehand. And the second value, is that the distance from point, or is that just the distance of the section?
Gotcha. Okay, let me answer it a little bit fuller. When you're trying to produce the shear diagram, you're only looking at the loading diagram. Everybody good at that? In order to produce the shear diagram, you look at the loading diagram. Once you want to produce the moment diagram, you're only looking at the shear diagram, right? So we're looking at the area of the shear, and the, area of a rectangle is base times height, right? And the base is 10 inches. So if you want, you could put the distances down here so you don't have to look back up. But the height is 120 and the base is 10. So it's 120 times 10, 120 times 25, 180 times 20, and 120 times 15. Does that answer your question, Angel?
Yeah, I definitely got it now. Thank you, Julie.
Okay, great. Okay, so I'm gonna stop sharing this now, but notice as the force goes down, shear goes down, force goes up, shear goes up. When the area in shear is negative, the slope goes down. When the area is positive, the slope goes up. Okay, and you could think of this as you did in calculus doing integration. You could also think of this, these curves are actually similar to those curves you did in physics 11 and 4A, where you were looking at the distance and then you did the velocity and the acceleration. Okay. All right. So I'm going to stop sharing this. And what I want to do now is share a different screen. And hang on a second. Okay, so the template we looked at, we saw the template, and then this is Tuesday's class problem. And now what I want to open up is this. This is shear and bending moment diagram summary of diagram shapes. So I'm going to open up that. That was not it. Yeah. Okay, let me move my pictures again. And I'm going to go down. Everybody take a look at the screen for a minute. This first page is a summary of all, but I separated it also. So we notice then when the load goes up and then the load comes down, our shear diagram goes up and then comes down. When our load goes down and then comes up, the shear goes down and then comes up. Okay. We haven't looked at distributed loads yet, but let's just take a look at this. A distributed load on a beam going down, it's a negative, so it's going to give you a negative slope. Does that make sense? So if we have point loads, the forces are positive, the shear diagram shows a positive. Force is negative, the shear diagram shows a negative. It's the same with distributed loads. Distributed loads, if the load is going down, it's a negative, it's going to show a negative slope. Let's take a look at the moment diagram. Everybody with me? When the area of the shear diagram was positive, our moment diagram was positive. When the area was negative on the shear diagram, our moment was negative. If our shear diagram has a negative slope, but a positive area, the shape is parabolic, but it goes up. If you have a negative slope and a negative area, it's still parabolic, but it's going down. I separated these into two different pages, but I think the first page is the best. So let's take a look at this. If you have a load diagram where the force goes up and then comes down, the shear diagram goes up and comes down and results in a positive area, and the moment results in a positive slope. If we have a force go down and then the force go up, the shear diagram results in a negative force and then a positive force, and it gives us a negative area and the slope is negative. And really what I'm doing is I'm taking the integral of the load to produce this, and then the integral of the shear to produce the moment. Let's look at these two distributed loads. They are exactly the same. Number 3 and number 4, the distributed loads are going down, which means the slope has to go down. But if the slope goes down with a positive area in the shear, the parabola is going up. If we have the slope going down, but the area is negative, we have a parabolic going down. Let me say that again. Distributed loads going down on a beam result in a negative slope, definitely. But when you draw it on the shear diagram, if part of the slope is positive, if the area is positive, you're going to have a positive parabolic curve. If you have a negative area, it's going to result in a negatively going down parabolic curve. And we're going to see it now. But this is the cheat sheet that I use, okay? Because I don't like to do integration. So if you don't like to do integration, you could have these cheat sheets. If you rather do it by the math, then do it by the math. Let me just show you two more examples. There are times we have triangular distributed loads. So if we have a triangular distributed load is going to result in a parabolic shape because this equation has an x in it, so it's going to be x squared. This one, we could also have a distributed load that's triangular, but instead of having a negative slope, it has a positive. Negative slope results in the parabolic shape going down. A positive slope results in the parabolic shape going down, but it's different. One's concave up and one's concave down. And then these are second order. So if you take the integral, you're going to get third order. So I just keep this sheet open for me every time I do a shear and bending moment diagram. Okay. And now we're going to do a diagram. All right. So I'm going to stop sharing. I am now going to turn me to be the host on the phone. I am going to hang on. Oh, this is the host now. So now I want to make sure that I am recording still. And I think what I'm going to do is I'm going to just put it on pause, it again. So now it's recording from my phone. Hopefully everything turns out good. Last week's Tuesday's turned out fine. Okay, so we're doing number 42 now. So let's take a look at 42. Okay, I'm going to draw it. 42 is on page 388. Everybody can see what I'm drawing? Yeah. So this is point A. This is point C. This is point B. This is 6 feet. This is 4 feet. On A to C, I have a distributed load that is 2.5 kips per foot. And at C, I have 12 kips going down. And then at A, I have a pin. So A is going to have an AY and an AX. And BY, B is a roller, so I have a BY. The first equation I'm going to do is sum of the forces in the X equal AX equals 0. So I know AX is 0. I'm then going to do sum of the moments about A equals 0, and I'm going to find out that BY is equal to 11.7 kips. And then I'm going to do sum of the forces in the Y equals to 0, and I'm going to find that AY is equal to 15.3 kips. And then I'm going to do sum of the moments about another point. Let's do it about B, and it's going to check out because I already checked it. So AY I know is 15.3 kips and BY is 11.7 kips. And the only reason why I'm not doing the whole equilibrium equations is you know how to do it already, and let's spend more time on the shear and bending moment diagrams. So I have 3 sections here, so I'm drawing the line down from 3 of them. I'm going to draw my horizontal line V. I'm putting kips, 0 plus or minus. And then I'm going to draw a line down here for moments, and the units are going to be foot kip, 0 plus or minus. And we're going to start in the middle because I'm going to start with Jordan. I'm going to start with you, Jordan. Okay. So let's take a look at this shear and bend, the shear diagram. So I have to figure out what my scale is going to be here, right? So let's see. We have a 15 kip, a 12 kip, a 10 kip, 11 kip. How much loading is in here? Jordan, how much loading is in the distributed load? Oh, and I should be pinning this, shouldn't I? Pin it. Can you see it bigger now? So Jordan, what's the load in this distributed load?
2.5 kips per feet.
Right, so it's 2.5 kips per foot, and how much feet are we going over?
6.
6. So what's the total load?
6 times 2.5, which is 15.
Right. And you guys, look at this. Think of it this way. It's 2.5 times 6. 2 times 6 is 12. And then what's half of 6? 3. So it's 15. Try to think of quicker ways to do the math. So we're going to be moving at 15. So I'm thinking, let's do, how about 5, 10, 15, 20? 5, 10, 15, 20. Okay, so Jordan, what do I do at point A?
That would be
I don't think you were here on Tuesday,
2.5?
Jordan. Say it again.
I was here for the first half on Tuesday.
Okay. I don't know if you watched the video, so you might need to pass. I didn't hear what you said.
I'll just pass.
Okay. Laura, what do I do?
You go up to 15.3.
Great. 15.3. And then I'm going to stop there. Okay, Laura. Liam here?
Yes.
Okay, good. Liam, is anything going on between A and C?
Yes.
There's the distributed load, right?
Yeah.
And is the force going down or up?
It's going down.
So we know we need to draw it down. Based on what those summary sheets or the cheat sheets I showed you, how is it going down?
Linearly.
Right, and is it, am I going back down on A or am I doing a diagonal?
A diagonal.
Right, so we said it was 15, so that means it's going here, right?
Yeah, to 0.3.
Right, 0.3. Let's just shade it in. Okay, Lise, are you here? Mackenzie? Marcine?
Yeah.
Okay, Marcine, so what happens when I hit point C?
You have to now incorporate the 12 kips load.
Right, and what do I do?
You're gonna go down. It's just gonna be horizontal and go down -12 from where you were.
Okay, you mean vertical, right?
Yeah, I meant when you draw it. I meant when you draw it to the next point, it would be.
Oh,
vertical.
okay. Okay,
Yeah.
so I'm gonna go down 12, so I'm going to 11.7, right?
Yeah.
Okay, and then from C to B, is anything happening?
Yeah, we go up 11.7 and we trace right back to 0.
I'm sorry, you're going faster than I'm going, so slow down a little. From C to B, is anything happening between C and B?
Oh no.
No, so what do I do?
You draw a horizontal line.
Great, thank you. And then what happens at B?
Then it goes up 11.7 and goes to 0.
Right, and it closes at 0, right? So we know it closes at 0, so we know that we checked our work.
Yeah.
Okay. All right, so now what's the next step? Maria, what's our next step now? We transferred all the loading information from the initial free body diagram down to the shear diagram, and now what do we want to do?
Now we go down to the moment.
Now we have to show the moment diagram. So how are we going to find the moment information? What do we need to look at here?
The area of the underneath the shear diagrams.
Right, so let's just call it 1 and 2 because there's only 2 sections.
Mm-hmm.
So notice when you calculate area 1, it's a triangle and a rectangle, right? You guys? So it's 1/2 base, which is 6, times height, which is 15, plus base, which is 6, times height, which is 0.3. Or we could have used it, did a trapezoid, right? This is the same as I could have also said an area of a trapezoid. So this I did the triangle, and then I did the rectangle, or I could have just done the area of a trapezoid, which would be 15.3 plus 0.3 over 2 times the distance, and we would get the same answer. And what do we get?
I don't know.
I got 46.8. Let's see if I got it both ways. Yeah, 46.8. Both of them came out to be 46.8. Okay, and then area 2 is base times height, and the base is 4 and the height is 11.7. So that comes out to be 11.7 times 11.7 times 4 is 46.8. Wow, how convenient, huh? I kind of did my check already. All right, so Maria, you're getting the hard question. Is this a positive area or positive? Well, so first of all, is the slope positive or negative?
Negative.
Okay, so the slope is negative. Is the area positive or negative?
Positive.
How about here? There's no slope, right? And is the area positive or negative?
Negative.
Negative. Okay, so I don't know. I'm curious from you guys, do you like just using the cheat sheet or you like to do the integration? I don't know. You guys want to tell me? Maybe put it in the chat.
I don't know if we're going to do integration formulas, but knowing the concept is probably useful because it's just summing up the area, right?
Right.
So it's the area at each, like, I don't know,
That-
slice.
That's
So you could-
correct.
Yeah.
So you could say the downward slope one has a bunch of positive area, then adds a little less, then adds a little less, then adds a little less. That's a way to see that it's going to be one of those curves rather
Okay.
than having to memorize the chart.
Great. Yeah. And you don't have, yeah, it's definitely. Did everybody get what Dave was explaining? That when you take the integration, the area is getting smaller and smaller.
So is
Okay.
that gonna be a curve down? So is that gonna be a curve down?
Well, I'll look at my cheat sheet. So if I have a negative slope and I have a positive area, it actually goes up. Oh, and I didn't make my scale, so I guess I'm gonna have to make my scale now. Hang on a sec.
Okay, but I don't think
Okay.
that graph should start at 0, right? It starts with a bunch of area.
That's why I'm confused.
Hang on a second. No, it starts at 0. It always starts at 0, always ends at 0. What we have going on here is we have a rectangular area and we have a triangular area. The rectangular area with a positive area would result in a slope like this. But the fact that we have this triangular area with a negative slope but a positive area, it's going to go up like this. So it's definitely going up. Hang on, 20, 40, 20, 40. Doesn't always, the moment always has to start with a moment at 0 unless we have a concentrated moment here. So if this is 40, this is 46. It's going to go like that.
Oh, because it's distance 0. Oh, because it's distance 0 at the start for a moment, right? That's why it has to be 0 at the start.
I just know it always starts at 0. I'm not really sure. I don't understand why you're confused. So I don't know what to say about that. And I think the
Definitely.
question you're asking is more of a calculus question, so I can't answer it anyway.
Okay, I'll think about it later.
Okay, thanks. All right, and then the second, where are Marcine, Maria, Matthew? Matthew, you here? No. Okay, Myra? Miles. Okay, Maria, we're going back to you. We have a negative area here, so what is it going to look like?
It's gonna be a negative slope down to 0.
Correct.
And this resultant must be continuous, no?
Say it again. Let me
The
look
resultant-
see your faces. Hang on a sec. Okay, Jason, what was the question? What's continuous?
I'm noting that the line that describes the sum of the area of the shear must be continuous.
So we start out with, I think I know what your question is. We start out with a moment of 0. And then this is the change in moment that occurs from this point to this point. So here's my change of 46.8. Then this area right here tells me the change in moment that occurs. And because it's negative, it goes down on the line. For right now, I am just doing this graphically, and soon I'll be doing it mathematically. How can I draw a line so straight without a ruler? I don't know. I just practice, I guess. Well, I keep my hand steady. I know where I'm coming from and going to. I don't know. But I'm just doing it graphically, but soon we're going to do it mathematically. So you guys are going to determine which one you prefer. So this is what's happening. So in terms of this problem, what is, Peter, you here? Tim, what's the maximum shear the beam is going to experience, and what is the maximum moment the beam will experience?
15.3
Kips.
Yep. And on the moment, 46.8 feet kips.
Right. So in this case, we know that we would have to design this beam. We would have to select a beam that can handle this shear in this moment. Okay, you ready for me to do the math now? I'm going to go back to this problem. Everybody could see it? Everybody ready? Actually, you know what I'll do is I'll fold it. I'm going to fold the page. And do it on the side. Okay, everybody ready? So when you do it mathematically, you're looking at the sections, each of the sections. Okay. Tony, you here? Victoria? No. Okay, Amani.
Yep.
Okay, how many sections do we have here?
4.
4. Okay, so I'm going to look at the first section, section 1, and I'm going to draw it. I'm going to call the distance x because I'm anywhere in this distance x, which means I'm anywhere between 1 to 10 feet. And at the left end, I have 120 pounds. Am I drawing this too small, writing it too small?
Just a little bit.
Okay.
Pretty teeny.
Now I want you to be able to see this too here. So section 1 is going to be from 0 to 10 feet. And at this point, I have 120 pounds. And this distance is x. Watch what I do for a minute. I'm going to put the shear going down, and I'll talk about my sign convention in the end, okay? So just believe me right now, this is the sign convention. What I'm doing is I'm cutting this beam anywhere. Everybody look up here, please. I'm cutting this beam anywhere here because I want to find out what the shear is that it's experiencing anywhere here. So I'm calling it X. And at the place that I cut it, I'm using C for cut. I'm putting a V going down in the moment. So I am not, you guys, showing the 240 pounds because, oh, let's not use C because there's a C point here. Let's call it O. At somewhere, at some point along here, I could cut it anywhere I want, but I'm not. I'm cutting it right before C. So this is the free body diagram I have for that section. There's 120 pounds going down. V, the sign convention is to draw it going down. We have to do this, the sign convention I'm giving you, to get the drawings we have. So I am going to do sum of the forces in the y equal negative 120 minus v equals 0, and the shear is going to be 120. That means anywhere in this section, the shear is 120. And then I'm doing sum of the moments about where I cut it, and it's 120 times x positive plus the moment there is 0, and the moment is equal to negative 120x. So now, using my highlighter,
Joanne,
I
think
left
we
out a
gotta-
negative sign.
Yeah.
Thank you. Okay, so now I did a free body diagram for this first section here. I put the cut at any point in here where X is 0. So now what I'm learning from the sum of the forces in the Y is the shear is always a negative 120. And I could color it in. The moment diagram in that section is negative 120X. So when X is equal to 0 at this end, the moment is 0. And when X is 10 feet, the moment is 1200 negative. And that makes my diagram go from here to here, and then I could color it in. So far, so good? Okay, let's do section 2. At section 2, now I'm cutting it here. So let's draw the free body diagram of that. Well, at the A, it's kind of like doing method of sections on trusses. We have to look at the whole left side. So I have the 120 here. This is 10 inches, actually, not feet. Here I have 240 pounds. This is X. And now I have my new shear and my new moment. So I drew a free body diagram that is going to allow me to calculate the shear and the moment anywhere within the section. Sum of the forces in the Y equal negative 120 plus 240 minus V equals 0 and V equals 120.
Hey, Joanne,
Some of the moments, what?
Can you move it up? Thanks.
Yeah, thanks. Some of the moments about that cut again is 120 times 10 plus X positive, 240 times X negative, plus moment equals 0. So that's 1200 plus here's my moment. Did I do the math right? So 120, 1200 plus 120X minus 240X. I moved the moment over to the other side, but that was kind of foolish. I should have just kept it on that side. So now I'm moving this over and these over. So this is going to result in, yep, this is right. So now for the shear diagram, I see that between this section 2, which is 10 inches rather, 10 inches to 25 inches in this section, V is 120. So it's 120, and then I could color it in. The moment, notice it has an X in it, right? So it's going to be a diagonal. So when X is 0, remember X is only the distance between here and here in that section. When X is 0, the moment is negative 1200, which checks out because it's already negative 1200. When X is 25, the moment turns out to be 120 times 25 minus 1200. Turns out to be 1800. And sure enough, at 0, it's 1200. At the distance of 25 feet, it's 1800. And this is linear because we have an X in here. It's a linear equation. How's everyone doing? Do you understand the concept? Jason, no? Lavoy? what you're doing is, remember method of sections, right? We had a truss. We had a truss and we wanted to find out this. So we broke the whole left side to find out what this force is, and this force is. We were trying to find the loading that goes along it axial, whether it was tension or compression. We're doing the same exact thing now. We're taking the whole beam and we're cutting it and looking at only the left side and determining what the shear and the bending moment is for each. We're doing the same exact thing, but in a truss, the load we were looking for was the load, the tension or compression that's axially transmitted through here, because these were two force members. This beam is not a two force member. So when we cut it, we're actually finding the shear and the moment at that point. The shear and the moment. So when I looked at the first section, I said, okay, for that distance of X, I draw the shear and the moment. You may not know why I'm drawing V down and why am I drawing V negative and moment positive? You don't know yet, and I haven't told you yet, and I'm not going to tell you until later. But so you're putting the shear because you want to know exactly what the shear is at any point in here. At any point in here, I want to know the shear. So it's a function of all the forces on the left. Just like when you did method of sections on the truss, the values, the forces in these members were a function of all the forces that were on it on the left.
Yeah, but except with the truss, it doesn't matter where you cut it in relation to the members. This does.
Correct. Correct. Good point. All right, did everybody hear that? It doesn't matter if we cut it here, the truss, or here, or here, or here. It doesn't matter because the type of loading that is in a truss member that's a two force member is axially going through here. But in this case, where I am along here totally could matter. Especially
That's why
if
it's
it's
changing. That's why it's changing. There's a variable X, and that will change
right
as you cut it in different places.
I'm keeping X in here because the shear could change. It just works out that in this problem, when there are only concentrated loads, the shear doesn't change within the section. So we're always going to get a number like V is equal to something, V is equal to something. But if we had a distributed load, the V is going to change as I'm in that section. In the truss, I'm finding the load that's along the member. In the beam, I'm finding the load that's perpendicular to the member at different points and the moment that is at any point. Okay.
So if we did that with a distributed load, we would get the shear having an X in it. It would have like a linear, like a line. And then the bending moment would have a square in it. It would have an X square, which is what gives you the curves. Is that it?
Correct. And
Okay.
we'll do that. So I don't know if you want me to keep going. Why don't you do it? All right, you guys do it. Section 3. So section 3 is, what is it, 35 feet? 35 feet to 55 feet. That's section 3. So maybe you want to label it. We already did 1, 2, 3, or 4 here. So we could just call it, section 1, section 2, section 3, section 4. So we have to draw so for section 3, we're cutting it somewhere. And this distance that we're cutting it is X. So I have to draw the whole thing. I have the 120 here at A. At C, I have the 240. At D, I have the 300. This is 10 inches, 25 inches, This is 25 inches. This is going to be X. This is where I'm cutting it. I put my V down and my moment like this. So now do it. Sum of the forces in the Y equal negative 120 plus 240 minus 300 minus V equals 0. V turns out to be 120, 180. Negative 180. And I should write units, but this is kind of scrapping away, so I'm not going to write units. And then some of the moments about the cut, it's 120 times 35 plus X, positive, 240 times 25 plus X, negative, and then 300 plus 300 times X plus M equals 0. So that's 120 times 35 plus 120X minus 240 times 25 minus 240 times X plus 300X plus M equal. You could see why I don't want to do this. I'd rather just draw it, but we're figuring out what it is. So 120 times 35 equals minus 240 times 25 equals, it's negative 1800. And then 120 minus 240 plus 300 equals 180. X equals M, but that means the sign's changing. Let me just check it. Yeah. Okay, so when X is 0, M is equal to 1800. And when X is, what's the distance X here? 20? Yeah. When X is 20, M turns out to be 180 times 20 minus plus 1800 equals negative 1800. Should I wait for you guys? Are you still doing that math?
Yeah, I'm still catching up.
There's two concepts I need to talk to you about besides showing you the math, but I mean, why don't I post this, you guys? I'll post the math so you can see how it's done. Okay, I'll make sure I post this.
Can you show what you got again for that one? Can you move it
Yeah,
over again?
I got, oh, you mean the diagram?
No, right there, that's fine.
1800 minus 180x. I didn't check it yet. So let's see, I got a negative 180 for, yep, I got the same thing. And then for X, 0 is, I got 18, and this is negative 18, yep.
Joanne, for the moment calculation, what do you do with the shear moment that you drew on your free body diagram?
Oh, when I'm calculating the moment about 0.0 where the cut is, the shear is at that point, so it drops out. Because when I'm trying to find the sum of the moments at this point, the shear creates no moment.
Oh, so that's where we don't find the moment from A, we find it from the moment.
No, I'm putting a subscript of 0. And I'm putting a 0 right where we're cutting. Okay?
Okay. And you
So
have
I'm
to,
always finding the moment about this point.
okay.
And you guys remember that a force that goes through the point I'm trying to find the moment about creates no moment. But if there's a concentrated moment on here, I have to add it in. Okay, so I think I would rather go on from this right now. So I showed you an example, and there are tons of math examples in the book if you want to do it that way. But you see that when I solve for the moment, I'm getting something linear because I was given concentrated loads. I'm going to talk a little bit more about this, the sign convention. Okay, is everybody with me? Again, I'll post the math. Okay, so take a look at this, our shear and bending moment diagram. If the force goes down, this is kind of a complicated topic, but I want to explain why this is the sign convention. When the force goes down, the shear goes down, right? So the shear diagram is the same direction as the force. The only way to get the shear to be going the same direction as the force is to start with the shear going in the opposite direction. So if I have a force here of 150 pounds and I want my diagram in shear to go down 150, I have to have the shear going down, because here some of the forces in the Y equal negative 150 minus V equals 0, V equals 150. Notice by having a sign convention of V drawn negative at the cut results in V having the same exact sign as the force that it has. I think it's wonderful that when you go down 120 up here, you go down 120 here. When you go up 240, you go up 240. When you go down 300, you go down 300. The reason this is the case is because we are choosing at the point of the cut the sign convention of V going down. If we had V going up, this whole shear diagram would be flipped. And when we go down, we go up instead. I don't know if you're following on that. So basically, I guess the thing is, it's complicated and you have to think about it a little. But we want to draw a shear diagram that has the shears going in the same direction. So we have to have the sign convention with the V at the cut going down. Then, when we have a negative V, we want our moment to go down. When we have a positive area, we want our moment to go up. When we have a negative area this way, we have to have the sign convention this way. So the sign convention of V drawn down and in the negative and the moment drawn positive allows us to get pictures like this. If the sign convention for V or M were swapped, the drawings would be opposite of these. Do you need to completely understand that? No. We just know we want the diagrams to look like this. And remember that you have to have V going down and M going this way. And it has to do with doing the signs. If V goes down and I do the sum of the forces in the Y, I have a negative 150 minus V, and V turns out to have the same sign as this force. So that's why we have our V with the sign convention going down.
If the initial force was going up, so if there's, then the shear would be opposite.
So let's see, if we had 120 pounds going up, we still, the sign convention has shear going that way. Sum of the forces in the y equal 120 minus v equals 0. V is equal to 120. You want the v to be drawn negative so that you have the sign that's given in the original force. Okay, so now spend more time thinking about that. Going back to this diagram. So if I did a cut, want to do another cut? Let's say we want section 1. Section 1 goes from 0 to 6 feet. I have 15.3 kips going up. And I have 2.5 kips per foot, and the distance is X. I put my V here going down. I put my moment going positive. I do sum of the forces in the Y equals 0, is 15.3 minus 2.5x minus V equals 0. V equals 15.3 minus 2.5x. So when x is 0, V is 15.3. When x is equal to 6 feet, V is 15.3 minus 2.5 times 6, which turns out to be 0. So it goes from 15.3 down to, actually, it comes out to be 0.3. Sorry, goes down to 0.3. How about the sum of the moments at the cut? Put it 0.0. It's 15.3x negative 2.5x times the distance, which is x over 2, positive, plus moment equals 0. Let me do this again. I'm doing the sum of the moments about 0.0. It would be 15.3 times x plus the force here, 2.5. The force is 2.5 times x, right? A distributed load is 2.5 times x, and it's halfway over on the x. So it's 2.5x times x, half of x, plus m equals 0.
Wait, I'm a little bit confused on why it's 15.3 times x. If we're doing the moment from the point where v is, wouldn't it always just be 6? Because isn't 15.3?
No, because this is x. I could be cutting it here, 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 anywhere. X represents the distance that I'm going from A. It's only when I do substitute x in, 6 for x, then I could find the shear at this point, 0.3.
Basically, you're not cutting it at C. Like that's
I'm
the whole
not cutting
point,
it at
right?
C.
Is
I'm
we're not
cutting it
at C.
anywhere
Yeah.
before C.
You're creating a formula to find what the value would be at any arbitrary point.
I'm creating a formula by doing some of the forces in the Y and some of the moments about the cut point. I am finding the formula for the shear, the value of the shear in the moment at any point between 0 and 6.
So early on, maybe I misunderstood it. You were saying the start and end of these diagrams has to be 0. It always starts at 0, goes up and down, and gets back to 0.
Correct.
But you just showed that it doesn't, right? You said x
No,
equals 0, there's a value.
Right, but it's only at the beginning of the shear diagram and the end of the shear diagram that has to close at 0. But anywhere in here, the diagram could have any value of shear. So I am looking at, I'm trying to find just this section. What is the shear and the bending moment at any point here? So I cut it. The sum of the forces are going to be equal to 0, but the shear isn't 0 except at the ends.
It's not, right? At 0, right? At the left end, it's 15.
Oh, I see what you're saying now. It starts at 0 and it goes up to 15. I'm sorry. Yeah. Yeah. I thought you meant over here. Yeah, it goes up. Yeah. Yes. You're drawing it up to 15. It starts here and it ends here.
Okay, well, maybe I'll ask about that later.
Okay. Okay.
I mean, but like mathematically, it's not really like it's the ends of the graph. You wouldn't really say are 0 mathematically.
Okay. Just remember that it's got to close to 0 when you get to the end. I don't know how you want to express it.
I agree that the moment one must be value 0 at the start and value 0 at the end.
Now, there's a
because of the
case where
distance
there,
thing.
there's
Is that
a
not
case.
true?
It's not true. There's a case, and we're getting to that. That's the second thing I have to show you. But I feel like this math stuff is just, I don't know. If you could draw the diagram without doing all these cuts, and the cuts are just confusing you, and you're bound to make a negative error, I just wouldn't do it. I would do the math if you want to check it. I would just draw the diagrams. But let me just finish this. So so this is moment is equal to, so it's going to be 15.3x minus 2.5 x squared over 2. So the moment is 15.3 minus 1.25 x squared. When x is 0, the moment is 15.3. Okay, I made a math mistake.
You forgot the x on the 15.3.
Oh, thank you. Thank you. Thanks, Laura.
No problem.
Oh, 0. Thanks. Okay. And when x is 6 feet, the moment is times 36 equals minus plus 15.3 times 6. 46.8. So then I got this curve now. Okay, you have 4 homework problems. Do it graphically, check it with the math. Okay, you could do this. It might be a little confusing, but you could do it. But I need to go on to another problem to show you something important. I'm gonna draw one here. Can you see my paper? Okay. Can you read my drawing? Is it too small? So the beam
It's okay.
goes from A to B. The distance from A to C is 0.6. Distance from C to D is 0.9. D to E is 1.5. And E to B is 0.2. There's a 40 kilonewton force going down, a 32 kilonewton here, 16 kilonewton here. A has a pin. So we have to calculate AY and AX. And B has a roller. So we have a BY. And notice there's a concentrated moment at point D of 15 kilonewton meter. So sum of the forces in the X equal AX equals 0. Got that one. Sum of the moments about A. Could everybody see the loading? So there's an AY, there's a 40 kilonewtons, a 32 kilonewtons, a 16 kilonewtons, a BY, and then there's a concentrated moment at point D that's 15 kilonewton meters. Sum of moments about A. 40 times 0.6 negative, 32 times 1.5 negative, 16 times 3 negative, BY times 3.2 positive plus 15 equals 0. You guys, this is really important. This textbook does not have a lot of problems in it with concentrated moments. Whenever there is a concentrated moment, you have to add it into the moment equation, no matter where you're trying to find your moment. Okay?
How does that show up in the moment diagram?
You'll see it in a little bit, but you could think about it. That's why we're doing this problem. Think about how a concentrated force shows up in the force diagram. So how does a concentrated moment show up in a moment diagram?
And a concentrated moment exists
Like if
specifically
you throw
at
a
that point.
Yep, like you're putting a
Gotcha.
screwdriver right in that point. Did anybody get BY yet?
Yes, I got that, but is it positive?
Okay, you got 32.8. Okay, so let's see if it's positive or negative. 24. Positive. Great. Thank you, Laura. All right, sum of the forces in the Y equal AY minus 40 minus 32 minus 16 plus 32.8 equals 0. AY equals 55.2? The forces have to go up anyway. Some of the moments about, let's do some of the moments about B. Well, I'm just gonna do a check because, Laura, did you get 55.2?
Yes.
Anybody else get the same answers as me?
Yes.
Who's the yes?
Amani.
Amani? Okay. Okay, they're fine.
Can
All
I
right.
write those in as checks on my homework? Can I just write Tim got
Tim
it?
checked it. Yeah,
I-
yeah.
I got 55 too as well. I think we're okay.
Okay.
All right, Tim check, Dave.
Okay, so I did blow it a little bit. What I should have done is drew all my lines first, right? So all my calculations would have been on the left. But now what I'm doing is just draw them down. I'll do them at the bottom.
Your concentrated moment there, 15 kilonewtons,
Yes,
was just added in. It doesn't matter where it is.
it just gets added in because it's like a couple. A couple gets added in anywhere. Two forces, same magnitude, opposite direction. No matter, if I had a ruler, Jason, if I had a ruler and I had several holes in here and I took a screwdriver and I stuck it in a hole here or here or here or here, the whole thing would be spinning that same amount.
So graphically speaking, it will raise the whole moment by that amount or lower.
Raise or decrease. Hang on. Okay, there's another little issue that we're dealing with. All right, so I'm drawing my shear diagram and my moment diagram. V kilonewtons, 0 plus minus moment foot kilonewton. Yeah, right. Kilonewton meter, 0 plus minus. So let's see, our shears are 40s. I'll do 20, 40, 0, 20, 40. Okay, who wants to do the shear diagram? Me. Come on, somebody. Me. Who? Maria. Start
Okay.
at 0. What happens?
We go up by 55.2 kilonewtons.
Right. Okay, then what happens from point A to C?
Nothing.
Nothing. Then what happens?
Then it drops by 40 kilonewtons. So you go down to 15.2.
Yep. Then what happens?
Nothing.
Then
it drops again by 32 kilonewtons.
okay.
I don't know what that is. Negative 15 point. Negative 15.
I think it's 17, isn't it? I don't know. 32 minus 15.2. 16.8.
Okay.
And then what happens?
And then there's a moment. Does that have anything to do with it? No.
Nope, because this is a shear diagram.
Okay. Then it goes over and then it goes down by 16 kilonewtons.
Then it goes down 16. So that's 16 plus 16 is 32.8.
Mm-hmm. Then it goes over and then it goes up by 32.8.
Great. And it closes. Why would anybody want to do all those cuts and math if you could just get it like this? But you could check it with the math. Okay, so what's the maximum shear, Maria?
55.2.
Right, so that's the load that I have to make sure that my beam can withstand. Okay, who wants to do the moment? Well, should we find the areas first? 1, 2, 3, 4. So area 1, area 2, area 3, area 4. Area 1, 55.2 times 0.6. Area 2, 15.2 times 0.9. 16.8 times 1.5. 32.8 times 0.2. I probably wouldn't do any rounding because you're gonna just get errors in the diagram. It won't close. So just bring it out. I'm bringing it out to 2 decimal places. Marcine, you want to do it?
Sure.
Okay. All right, so you see the areas here. Can you read them?
Yeah, I can read them.
Okay, so this is the areas of the 4 sections. So I start at 0 and what happens? Oh yeah, let's put positive area, negative area, negative area. So what happens first?
You're gonna go up to the first, which is 33.1, or you should make a scale first.
Yeah, let's do, should we do 2040 again?
Yeah,
Because I don't have a lot of room on my paper. Okay, so what is it going up to?
to 33.12.
33.12. Does everybody realize you don't want to round? Because you're not going to close at 0 at the end. You may not, so keep it. Okay, Marcine, what do we do next?
Now we want to go up another 13.68. So that's 46.8.
And let's just keep it with a 2 decimal places, just so that we're consistent. And nobody knows we know we round. Okay, so now here we come into the issue. I'll wait for everybody to be ready. When we're interested in doing the shear diagram, we look at the load diagram. Once we draw the shear diagram, we don't have to look at the load diagram to do the moment, except if there's a concentrated moment. So what I always do on my paper is if I see there's a concentrated moment, I put a little tick mark here at the spot. So I remember that I have to do something special here. Okay? Because otherwise, when I'm doing my moment diagram, I'm just going to use my shear diagram. And what's going to happen? It's not going to close. Think about it. If this is a negative area of 25, it's going to go to here. So 25.2 is going to give me 21.6. And then I have a negative area of 6. And I go down 6, and now I'm going to be at 15. You're going to see it's not going to close. So you could wait till you don't close and then say, oh, something happened. Or what I always do is when I see a problem that has a concentrated moment, I put a little marker here to remind myself. So I get up to here, and I say, oh, okay, there's a concentrated moment. When there is a concentrated load, there's a direct vertical change in my shear diagram, right? When there's a concentrated moment, I know Isaac's been chomping at the bit to say this. When there's a concentrated moment, what do you expect to happen here, Isaac?
I expect the
Let me
well,
just say
Dave
it
and I were
again.
arguing. Dave and I were arguing about it.
Okay,
We're
hang
not
on a
sure.
second. So when I don't want a positive or a negative answer right now. When there's a concentrated force, you have a vertical change in the shear diagram. When you have a concentrated moment, what do you expect to see here?
Vertical
Dave wins this
change.
one.
An instant change at that
A
spot.
vertical change, an instant change. So now the question is it positive or negative? So let's look. With the shear, you go up, shear goes up. Go down, you go down. The reason for that, I know class should end, right? The reason for that is because, where are all my papers? The reason that when you have a force going up, your shear goes up is because you chose the sign convention of a negative V. But what sign convention did we choose for the moment? A positive moment, which means the direct change of this concentrated moment is not going to be in the same direction. It's going to be in the opposite direction. So is this, Isaac, is this a positive or negative moment? Can you see it?
I think we're all struggling with the
Did-
positive.
did you
negative
say we're
here.
switching it now?
Negative, right?
Yes.
Because it
Yeah.
has to be negative because otherwise you will not get back to zero.
Yeah, but that's not really that's not the answer why.
No, I know
We have
that.
to
I'm
shift-
just saying.
But Tim's making some sense. We noticed we ended too high, so we must subtract it. But the reason why
Okay.
I don't know, I know it's hard to understand.
So we've just
you
chosen,
guys,
we
wait,
basically, we have
wait.
to realize
Isaac,
we
shh.
switched convention.
When you do sum of the forces in the Y, plus, minus, plus, minus, plus, minus, in the end, you subtract V because V is negative. And in the end, V turns out to be the sign, the cumulative sign of this. Because we have a negative sign convention for the V turns out to be the exact same sign of all the forces. The convention, though, has a positive moment. So when you do sum of the moments, you're going to say plus M equals 0. And then when you move M here, M is negative, which means the positive M is going to have a negative of whatever you get here. I don't know how else to say it. And maybe watching the video again will be like, oh, now I get it. If you don't want to get it, you don't have to. You just have to know. You go up in force, you go up in shear. You have a positive moment, you do a negative moment. We go down 15. So if we go down 15, we get to here, 31.8. So there's a direct change and it's a down. It's the opposite of the moment. Okay, Marcine, you want to finish? What happens in section 3?
It's a negative area, so we go down 25.2.
Right, so we go down 25.2, and what do we come out to be? 6.56.
56. And then the last
Is
area.
that right?
I got 6.6, but I know it's supposed to be 6.56 because I
Right,
think
so-
there must be a rounding error somewhere.
Okay, so let's find it. Let me just check my math. I bet the error is here. 55.2 minus 40 minus 32 minus 16. No, that's right. $46.8 minus 15 is 31.8 minus 25.2. I don't know where the error is, but there's some error here. Okay, and what's the last part?
Then we just go down.
Closes at 0.
6.56 to 0, yeah.
Okay, and what's the maximum moment?
It's the 46.8.
Right.
Or
So there's a math error here. I just don't know what it is. Where it is. There's a 0.4 off. All right, so now I know I'm going over. I want to hear from you in terms of, are you comfortable with drawing the diagrams? Thumbs up. Come on, turn on your pictures. Give me a thumbs up or something. Raise your hand or something.
I think I'm comfortable following the steps, but I have a lot of like reasons why questions, but that can be
Okay.
office hours.
Okay. This topic of shear and bending moment diagrams will be covered in strength of materials as well. Some people don't even teach it in statics, but I like to teach it in statics, include it, and you'll see it again. And if you wind up not taking strength of materials at Cabrillo and you transfer the 4-year school and take it there, you're going to be among students who don't know how to do it. Okay. So I think the only trick you have to remember with drawing it is that if there's a concentrated moment, you have to draw the moment, a vertical moment, and it's going to be opposite the direction of the moment that's applied. Okay, that's the only trick with the drawing. I think the other thing that was confusing was actually breaking all the thing into sections to check. Okay. All right. Lastly, then, let me now host Okay, I'm making me the host, my laptop the host, because I want to go to the overview. So I'm going back to the module and I'm opening up the overview. Okay. In this module, you learn how to solve for the shear and bending moments along all points on a beam and draw the shear and bending moment diagram. Okay, you will learn how to use the following steps. So the first step, I need you to clarify whether you think this sounds good or not. Solve for the reactions of the supports. Then you draw the beam and the loading on the beam. And then you draw lines down, maybe I should say vertical. Hang on.
I think down makes it pretty clear.
All right, well. Draw vertical lines down from the beam for the shear and bending moment diagrams. Then draw a horizontal line for both the shear and the bending moment. Put V, the units, plot 0, plus and negative, and the scale of the shear and bending diagram to the right of the line. Wait, put.
Maybe the vertical lines like clarify that it's from the forces too on acting on the diagram. Like,
Do you want me to change the wording? Is it okay now? Draw vertical lines down from the loaded beam. How's that?
I mean,
Maria?
Sure.
Okay. Okay.
Yeah.
Draw horizontal lines for the shear and bending moment diagrams. Put V units 0 and plus to the left of the line and put the scale of the V diagram to the right of the horizontal line. Watch lecture video for details. Do the same for the moment diagram. Put M units blank and the scale. Okay, 5. Using the loading shown on the beam, draw the shear diagram to scale and show the shear values on the diagram. As the loading goes up or down, the shear diagram is drawn up or down. A concentrated load results in a vertical change on the shear diagram. A distributed load down results in a slope line down on the shear diagram. Report the maximum shear. Then calculate the area of each section of the shear diagram. This represents the change in the moment diagram. Follow the shear and bending moment summary of the shapes file posted in the module. Report the maximum moment. I think I want to add in here. If there is a concentrated moment on the beam, you will need to show a vertical change in the moment diagram at that point. If the moment applied is positive, the moment diagram shows a negative change. Negative. You understand what I do when I have these parentheses, right? Okay, and then report the Vmax. Any edits to this? Are you guys good? Okay, so back now to the module. So you have the overview, you have the template, you have the shapes. You could look at the ones on the steel diagram. Here was Tuesday's class problem. I'll put Thursday's in right now. I made a video just in case I was going to be late for class, but I didn't publish it now, so I took it off, so don't worry about it. And then you have a homework. Okay, and then tomorrow in lab, you're going to be practicing shear and bending moment diagrams. And if you want Rob to go over the math, have him go over the math with you. I really like that both Rob and I are teaching because he does teach things a little differently than I do, or has a different approach on some things. And I think it's really helpful for different learners to learn from two different teachers. And then remember, you could always get help from Karen as well, and Andrew after lab class, and even Carl. Okay, I'm going to stop sharing and see, do you guys have any questions? Okay, so I will be in office hours today, and I'll be in office hours tomorrow. Okay,
Thanks so much. You're the best.
thanks.
Going overtime, making it work.
Okay, all right.
Thank you.
Have a good one, Joanne.
Okay, you too. Okay, bye.
Joanne, I do have one question related to the
Wait, I will
interview.
leave. Yeah. Jason, stay on. If you have questions, I'm okay. I'm available.
Cool. So yesterday I read the introduction again. So you said when you have a grade on the interview, the second interview higher than the first one, you'll get replaced. What if I did like terrible on the second one, I did like awesome on the first one?
You're
So
gonna have.
will that-
I'm not gonna replace the second one with the first one, but you're gonna have to prove to me that you know the material. So we're gonna have another interview, and I'll have some other opportunities. I just haven't figured out what they all are yet.
Awesome.
Okay.
Cool. Thank you.
Okay. All right. See ya. Marcine, do you have a question? No. Jack?
Sorry about that, Joanne. I had left just.
Oh, that's fine. I'm trying to figure out whether I actually recorded. Yeah, it looks like I recorded.
Yeah, it said you were recording most of. Every time I looked
Okay.
up, you were recording.
Okay, thanks. So I have to shut it off now.
Oh, Joanne, I did have a quick question about.
Yeah, do you want me to stop recording first? Oh, here, I
Oh.
see it up on the screen.